introduce. Great. Okay, so this next lecture and this next course will be given by Mateusz Michalek, and he'll be telling us about complete quadrics. So I'll let him get started.
Thank you very much. It's a great pleasure and a great idea of the organizers to organize such a workshop. I hope it will work out. So Tim not only will be noting questions, but he also told me that he will try to be available as much as possible during different breaks. I will also try to be available during breaks, but please feel free also to ask him all questions you might have, or he will be also correcting all the mistakes that I make and so on and so on. So you may contact either me or Tim. Let me start. So I will work over complex numbers, so that will be for the whole talk, and I will not even mention it. And let me start with motivation for the first few lectures. Let's say we have 4 general lines in the 3 space. And by 3 space, I usually mean the projective 3 space. And the question that I would like to ask is like, how many lines intersect all, well, each of L1 up to L4. Okay, so that's a question, and the answer to such a question could be 0, infinitely many, and so on. But it's some number as long as you assume those to be general. And the aim of the first few lectures will be to give you tools to answer such a question. And the way we will do it is, instead of the question how many, we will first look at a geometric version of this how many questions. Namely, we look at the Grassmannian G24. So for me, this is the notation for a Grassmannian of lines P1s in P3. I denoted by G24. And inside of this, there is a variety of, let me call it VI, so that X belongs to a VI if and only if the line that corresponds to X intersects Li. Okay, the Li line. And now our question is basically reduced to understanding the intersection, V1 up to V4. Yeah. So if we will be able to know that these are points and know how many points, the number of those points, the cardinality of this set is the answer to the original question. Okay, so this is the motivation, and to somehow develop the tools that will be needed, we will first introduce the Chow group of a variety. Okay, so because, as you can see, we will be interested in varieties somewhere, this motivates us to look maybe at all subvarieties. So for me, a variety will be irreducible. So let X be an irreducible variety. And we will first introduce the group of algebraic cycles. That is freely generated by all irreducible subvarieties of X. Okay, so what do I mean freely generated? There is one basis vector if you want to talk about basis of free modules. There's one basis vector for every irreducible variety. And then you can associate an integer to that vector, and the finite sum of such things is an element of Zx. So I would not like you to lose you here. Are there any questions about this? Okay, no
I have
questions.
one.
If there
Sorry.
are, yes, please.
So X is a variety in a projective space, right? So we think about it as embedded in a projective space, or
all of the varieties we will be considering, in fact, they will be projective varieties, but a lot of things I say work in general.
Okay.
So they don't have to be, it does not have to be a projective variety.
Okay.
Okay.
Thank you.
Okay.
So a sum of these is sort of a formal sum of
something like 2y1 plus 3y2 minus 5y3. All of those y1, y2, y3 have to be irreducible, but they can be of different dimensions. This is example of an element. Okay.
And now, we are disregarding dimensions and codimensions.
Currently, yes. We will get back to that soon. So now a Chow group A of x is, so Z of x somehow remembers too much. It's too big. So we want to divide it by something. This is called rational equivalence. And I will now define this. So now we define rational equivalence. So it's a subgroup of cycles, and I just will give you generators. So I have to write some combinations of irreducible varieties and tell you this is 0. So this is a separate definition for rational equivalence. Okay, and it goes as follows. We look at P1 times x. So this comes with a projection to P1, okay? And we take any irreducible subvariety here. So this is irreducible subvariety. Well, the only thing is that we don't want the image to be a point. So we assume it's not contained in a fiber. But otherwise it's any irreducible subvariety. And P1, I will say that it has two distinguished points that I will denote 0 and infinity. Well, formally it's 0, 1, and 1, 0. So this defines two subvarieties of x. Namely, we have Z0, which is Z intersected, well, with one fiber, so formally it's 0 times x, and I regard it as a subvariety of x, okay? And then there is the infinity, which is Z intersected, well, the infinity point times x, and again, I regard it as a subvariety of x. So this rational equivalence as a subgroup is generated by Z0 minus Z infinity. So we say that these two are equivalent, okay? So if you have your family, every fiber looks something similar to Z0 or Z infinity, and we identify all those fibers. We say that in the Chow group, they are the same, okay? So this is a very important definition of a Chow group. If there are questions, if something is completely not clear at this point, it might be good to ask. Yes?
Can I ask you to just, like, when you're finishing a slide, can you just press for like 5 or 10 seconds so that people can actually read, like, write whatever. I mean, it's a kind of hard to actually write what you're writing if you're just,
Okay, so by the way, I'm not writing anything that is not in the lecture notes. So don't worry, you didn't copy anything. Everything is in the lecture notes also. But okay, so I will pause now for 3, 4, 5 seconds, and
make it
and by the way, I will ask for questions. So any questions about the Chow group?
I think maybe I'm just a little confused about how this is sitting inside of the other group.
Yeah, so this is like 1 times Z0 plus minus 1 times Z infinity. very formally. So it's a combination of subvarieties. Okay, now to be honest, I'm slightly cheating here because I should say that these are schemes, but this is set in the lecture notes. If you imagine them to be reduced, irreducible subvarieties, then this is completely formal. Okay, so I'm just saying that all of the fibers, they are equivalent. They are the same, because this is the same as saying that Z0 is equal to Z infinity in AX. So because this is after division, we will write classes for that. Okay. Okay, so can I go to the next slide?
Another question, maybe?
Yes. Yep.
Is it clear that Z0 and Z infinity are irreducible?
No, they can be reducible. So let me, okay, so they might be even not reduced, which is even worse. So okay, so if there is a question about that, let me say. So if we have a reducible variety, let's say Y, which is a union of Y1 union YK, we will write that Y in A of X, the class, is the sum of Yi's. Okay, so these are irreducible components. Okay, and one thing that I wanted to hide, and for which I'm sorry, is that if you have a non-reduced structure, non-reduced Y with multiplicity, let's say M, then you will write that the class of Y is M times Y red. If what I wrote here does not make sense to you, don't worry about that too much. Okay, there are many questions. Tim gives examples. Okay.
Just ignore that.
Yeah. So if you have a line tangent to a circle, the intersection is not really a point, it's 2 points. But this I can give a formal definition maybe during a break. It's not so important for the for getting the big picture. Okay, so now we come back actually to one of the questions, that Zx is graded. It is graded by codimension. Yeah, so in other words, what I really mean is that there is a sum like this from k equal 0 to dimension of x, where the zkx these are subvarieties of codimension k. And what is important, but this is again something that one would have to actually prove, is that this descends to the Chow group. That is, you cannot have, you will never identify these fibers. They will be always of the same dimension or codimension. So actually, this descends to A of x, which is a sum of AKX. Okay, so AKX, you should think about elements here as classes. Well, formally, this will be combination of classes of subvarieties where codimension of Y in X equals K. Okay. Any questions about this? So probably I now give you those this time that Alessio asked about to copy, and I think it's time for an example. Yeah. I bet everyone would like to see an example. Okay, so an example. example is as follows. We take the variety that is just the projective space. Okay, so maybe that's a good point for me to ask you a question. Can anyone give me a subvariety of codimension k? So I would like anything that is codimension k. Anyone can give me something? There is one answer.
A linear space?
Yeah, so a projective subspace, yeah? So pk, okay? Well, but there are many of those, okay? It's not that there is one P1 in a P3. There are many, you agree? So, but in some sense, they are all the same. This I think you agree. And this is in fact a formal statement. They are all rationally equivalent. So what I'm saying is that this is a well-defined element of, I said codimension k. So this should be n minus k, Pn. Okay. Okay, so this, to write this, I don't have to specify Pn minus k, because you can always build a P1 and join any k-dimensional subspace with another k-dimensional subspace. So what is maybe less trivial, but I will give you also general theorems from this, is what from this it follows, is that this piece is actually isomorphic to Z. Okay. So the degree k part of the Chow group, this is just Z, where the generator is Pn minus k. So if you take any subvariety of codimension k, it will be rationally equivalent to a few times a projective subspace. And if you exactly want to know what is this a few times, then you have to look at the degree of the subvariety. Okay. So this finishes the Chow groups. We are now all experts with Chow groups, and now we play more. We go to Chow rings.
Maybe before going to Chow rings, we might see if there are questions on Chow groups, I guess. Sorry, I'm just slowing you down from time to time. But.
Is there a way we should sort of intuitively think about rational equivalence?
One intuitively should think that it identifies subvarieties that are more or less the same, or if you don't like more or less, so that they intersect more or less in the same way with other subvarieties. Or if you are a topologist and you like cohomology, you should think about it as homology classes. Yeah, actually, this rational equivalence is not very different from the equivalence in topology. Okay, so don't worry, a Chow ring will be just a Chow group. It's just that we have to define multiplication. Okay, this is what the difference between ring and group. And what will be this multiplication? This also explains why we graded this by codimension, because this should correspond to intersection. So the idea is that y times z should be the class of y intersected z. Well, of course, this doesn't make sense if you don't put any restrictions of representatives, because it could be not of the correct codimension and so on. So for that, we need to say that y and z, that y and z intersect in a correct way. So let me take the new slide. So this is a formal definition. What does it mean to intersect well? If we have A, B subvarieties of smooth. So from now on, our variety X will be always smooth. And it's quite an important assumption. So AB subvarieties of smooth X intersect transversally. So I'm defining transversally at a point P in A intersection B, if and only if the tangent spaces at A together and the tangent space at B, they give you the tangent space to X. Okay, there is always, of course, an inclusion, but we want equality. And we say that A and B intersect generically transverse. If for every general point of every component for every general point, let me put it P, of every component of A intersected B, they intersect transversally at P. Of P, the intersection is transversal. Is transversal. Okay, so you picked a general point of any component, let's say a random point for every component. You compute the tangent spaces, and you want to have TPA plus TPB equals TPX. Okay, so this is the intuition about that is like they intersect nicely. Okay.
Sorry, question.
Yes.
Is this sum as vector spaces? So we are viewing this tangent space as a subspace of a common bigger.
Yeah, so you can assume that your point P is a zero of a vector space, and you can all of those are subspaces of TPX, of the tangent space at P to X. So TPA is a subspace there, and TPB is a subspace there, and you want them together to sum to TPX.
Thanks.
Okay. So now a theorem, which was for, I think, 100 years attributed to Chow, but then people realized that the proof is not complete and actually referred to Fulton. So the assumptions is that X is smooth quasi-projective. So smooth is important, but actually we will always work with projective. So quasi, I will put in brackets projective. Then there is a unique product structure on the Chow group such that if A, B are generically transverse, then, well, if you take the class of A times the class of B, this is the class of A intersected B. Okay? So this means that what we want exists, and it's a highly non-trivial theorem. I mean, it would basically take the whole 5 days for me, I think, to prove it formally and to develop the whole theory. So that's why we will not do that. We'll just take it for granted, and we go forward. Okay?
Sorry, Mateusz, but when you say, like, when you have these statements about intersection and so on, do you, I mean, I remember this was the moving lemma, or I
yes.
mean, okay.
Yes.
So, I mean, if we just have the representatives in the formal sense, how do I know how they intersect? Like, am I choose? I mean, I guess that the original idea was to kind of wiggle the varieties so that they kind of intersect in a nice way. But
yeah, so that was the original idea. And as said, for 100 years, people believed it works. But actually, to prove that it works, you have to first prove this theorem. So actually, everyone for 100 years was making circles.
Okay,
So
then
if you are given a class, it is two classes, it is highly non-trivial to prove that you can put them in such a position that they intersect generically transverse.
Okay, so but then I guess I have another question, because I mean, when you're speaking of the Chow groups, you're dealing in the Chow rings, you're dealing with classes.
Yes.
But the definition of like intersecting transversally and also intersecting generically transversely does not depend. I mean, it's not defined on the class. It's defined on a given variety with a given embedding.
Yes.
Is that okay?
Yes.
So
you never say that two classes intersect generically transversally. So look here, I fix A, B that are generically transverse, and then a class of A and the class of B. You can say how they multiply.
Okay.
Okay. Okay. So then farther, one more then. Well, the AX.
Yeah. So wait. So there was a comment/question in the chat. So to verify that. So indeed. So that any two. Also, the question is: so do any two distinct classes in AX necessarily have representatives which intersect transversally?
No. It's not that you can move everything, but no. But the thing is that you can sometimes add something to a class and move it. So even if you know what can be moved, it's still a non-trivial theorem. So it's for example even not obvious that it uniquely characterizes the product, because maybe there are classes that you cannot move. Okay.
So does that mean it's not possible to multiply any two elements?
Well, no, in a ring, you can always multiply two classes, but it does not mean that you can find representatives that will intersect transversally. Okay, so if you happen to find representatives, then it's fine. Okay, that intersect generically transverse, then you know how to multiply. But in general, it could be quite hard to multiply classes. Okay.
So
okay, and
sorry,
then this becomes
Mateusz,
yes.
Correct me if I'm wrong. So that kind of means that you have the Chow ring, which is, I mean, you would like to think about that as, well, when I'm multiplying, I'm actually intersecting varieties, but that's only half true somehow, because the ring exists and is like formally defined, and the multiplication can always be done. But some of those multiplications can actually be traced back to this idea, but it kind of goes, I mean, you need to have the actual variety, the actual embedding to actually talk about that.
So the reason why you actually have to multiply classes, I can give it to you during the break, because sometimes if you multiply a variety times a variety, you get something negative. So of course you cannot put them in the transversal position, because no two things intersect in -1 point. But the classes still multiply. It's just you will never be able to put them in a generically transverse position. Okay. Then this is a commutative ring with unity. Commutative graded ring with unit. Okay. Any question about that? I mean, there were many, but
okay. Who's the unit?
Well, the unit is the class of the variety itself. So if you intersect with X, nothing happens. That's the one. So maybe I will write that X is 1. It's codimension 0. Yeah, the only thing of degree 0. Okay. Now, good news is that I already introduced now a lot of objects. So recall that I'm assuming that that our variety is smooth. So this is also known as the group of divisors. So the divisor class group. If you heard those names, divisor class group or Picard group. So to say that all these are the same, again, I recall that X is smooth. Okay, so these are classes of codimension 1 subvarieties, formal linear combinations of them modulo rational equivalence. Okay, so now in time for example, I hope. So we go back to xpn. Okay, so what happens if we intersect? So let us psi a be the class of this Pn minus a. Okay, so what happens when you intersect two spaces, general subspaces, one of codimension A, the other one of codimension B? That's a question for the audience.
Do you get the smaller of the two?
Well, I don't know. When I intersect two lines on a plane, do I get the smaller of the two? What happens when I intersect two general lines on a plane?
You get a point?
That's correct. So what will happen if I intersect something of codimension A with something of codimension B? I will get something of, well, some people are writing, I hope they are writing A plus B, which is almost correct. We need the assumption that they intersect at all. So A plus B is less or equal than N, and 0 if it's bigger. Yeah. Okay. And this one will be generically transverse if you really choose those projective subspaces in the general position. So this tells us that this is just this ring where X is the class of the hyperplane. Okay, so X is psi1, a class of the hyperplane.
I have a question.
Yes.
So in this case, the class of an hyperplane generates the Chow ring as a ring.
Yes.
So is it always true that A1 generates the Chow ring? Of
no.
No. I see.
A lot of questions that you might ask about Chow rings will be either not true or unknown. In particular, the millennium problem is to understand how it sits in how it maps to cohomology. But fortunately, yeah, often understanding this degree 1 part is enough. Okay. So now there are two very important operations on Chow rings when you have a map of varieties. So the first one, for this, we assume that F is proper. Okay. Okay, and then there is a morphism of groups. Groups, I repeat. So it's called the push forward. Okay, and it's defined as follows. So if you are pushing forward a class of a subvariety of X, there are two things that can happen. Either the dimension of f of z is smaller than the dimension of z, in which case you say that the push forward is 0, or it's a finite map. So f restricted to z is generically finite. General fiber, let me write it like this. General fiber has cardinality d. And then we just define it to be, well, the class of f of z, but because we had it a few times upstairs, so we multiply by d. Okay, well, non-trivial that this is a morphism of groups, the thing that I have defined. Actually, we need to extend it linearly, yeah, because I only defined it on classes of z. But it is really important that this is not a morphism of rings. Not ring morphism. Morphism. Okay.
Sorry, can you go through the definition again, because I think I lost you on this.
Yes.
One.
So we have z in X, yeah, and we look at the image of z, yeah. It could be of the same dimension, or it could be of smaller dimension. depending whether the general fiber is infinite or finite. If the image of Z is of smaller dimension than Z, then we by definition put the push forward to 0. And if the image is of the same dimension as Z, what we need to do is we need to look at the cardinality of a general fiber. So what we should imagine is that we have this image of Z and a few copies of it upstairs, D copies. And then we put the push forward of Z to be D times the class of F of Z. This should slightly improve viewing. Okay.
Okay, so you're saying that if the dimension of f of z is smaller than the dimension of z, you just set it to 0.
I just set
Otherwise,
it to 0.
if the dimensions are equal, you set it to d times the class of f of z, where d is the cardinality of the general fiber.
Yes, so
okay.
It basically naively you are counting how many copies of this Z, if this would be a covering, you are having upstairs.
And this is what, I mean, you're assuming f. I don't remember what proper means. Is it like an assumption, or is it the
it is an assumption.
Okay.
It is an assumption of a morphism. It is a non-trivial assumption, but if you're dealing with projective varieties, it's a trivial assumption.
Okay.
Okay. Okay. Now notice that this because we can always map X to a point. So let's say that X is projective if you want this to be a proper map. Then we have a push forward. We have a push forward from a dimension of X to a0 of a point, which is Z. Yeah, because we are looking at codimension 0 subvarieties of a point. And this is known as the degree map. So in other words, if we have something, a class of codimension equal to dimension of X, it is possible to associate to it an integer, so to talk about the degree of that. Okay, if this will be just a class of a few reduced points, you will be just counting those points. And typically the notation for the degree of some class alpha is integral over X of alpha. Okay, so this is push forward. Now there is one more very important definition. When I was young, people were defining it for flat maps, but currently they define it in full generality. So, so we have X morphism of varieties, and then we have a pullback from A of Y to A of X. Okay. Now the good news is that this will be a ring morphism, and on the other hand, defining it's quite hard, but it is in many cases easy. So if you want to know what is a pullback of the class of Z, this is just the class of F inverse of Z. If very, very weak assumptions are satisfied, so either F is flat, if either F flat. So if you don't know what F flat means, don't worry too much. It just means that the fiber are not very different. Or actually when Z is Cohen-Macaulay and F inverse of Z is of correct dimension. Okay, so what do I mean by correct dimension? Maybe I can still fit it here. So I want this to be a map of rings, to be a ring morphism. Okay. Now, the fact that some assumptions are needed for that, if you know blow-ups, consider a blow-up of a point, and different things will happen if you take a point that you are blowing up and the point that you are not blowing up. Okay. Any questions?
So you said that, I mean, for the push forward, we had that definition that was just a group morphism.
Yes, and this is a ring morphism.
Whereas this one is a ring morphism. And this definition you gave is basically saying that any class of subvariety is going to be sent to the class of the pre-image.
Exactly.
And that, I mean,
actually, that was a definition when I was young, and everyone was assuming that F is flat. And so then this comes for free.
So this is the way we should think of that? Is it also the intuition behind the...
Yes, this is the intuition behind it. You just take the pre-image.
Okay.
Okay. Okay. I will finish this part with an example. So consider two curves in P2 of degree Z1 and Z2. So Z1, Z2 curves of degree D1, D2. Okay. Well, this means that the class of Z1, this is D1 times the class of P1. And the class of Z2 is D2 times the class of P1. Okay. Now, what happens if we intersect this? So we multiply the classes. Well, assume Z1, Z2 intersect transversally. Which in this case just means they are not tangent. And then we know that this is equal to, well, from one hand, this is equal to the class of Z1 intersected Z2, but on the other is D1 times D2 times the class of a point. Yeah? So we see that then they have to intersect in D1 times D2 many points. That's Bézout theorem. Okay.
So the hidden step is that class of P1 times class of P1 is class of a point.
Yes, but we did that already for Pn.
Yeah, no,
so
I'm just saying
P2,
that because I
also
mean,
know that.
I just wanted to say out loud why there is a class of point.
P1 times P1 is a class of P0, yeah. Okay. I still have a minute. This is what my clock says, so I will maybe not lose it. And I will give you a definition of a stratification that will help you to compute Chow rings in general. So a stratification of a variety X is a finite collection of irreducible, locally closed. So locally closed means an intersection of a closed and an open set, which is equivalent to the fact that at every point there is a neighborhood such that it is closed. Locally closed subvarieties such that two conditions hold. Well, first, X is a disjoint union of the UIs. And second, the closure of every UI is a union of some UJs. Okay, and with this, I will finish the first part of the lecture. I'm, of course, very happy to hear questions. Hello, hello. So we start with part 2. So I just said that what is a stratification, which is basically a reasonable subdivision of X into subvarieties that could be, well, they are not closed, so I will not call them subvarieties. And actually, I call them strata. So UIs are open strata. And their closures are called closed strata. Okay. Well, I can still write here while people are coming. So if each UI is an affine space, it's isomorphic to some affine space of whatever dimension, then the stratification is called affine. And I think in this lecture, we will only deal with affine stratifications.
Does it need to be the same affine space, like the same dimension?
No. They will almost never be the same affine space, because it's like you know, they are in the closures of each other. So if you take the closure of one, it's covered with the others. So these UIs are of different dimension. Okay, so this is like K of I. Okay. I plan to go to the next slide, where I will say that if you have an affine stratification, everything is easy and beautiful. Okay, so a theorem. So I cannot see Tim, but he was always telling me when to go to the next slide. Okay. Okay, so let's say that X is quasi-projective. With affine stratification. Then the classes of UIs form a Z basis of AX. Okay, so if you have an affine stratification, you have a complete description of the Chow group, not as a Chow ring. This I didn't tell you, and that it's of course non-trivial, but at least as a Chow group. And again, the proof is highly non-trivial in general of the statement I have provided. This is due to Totaro. The fact that these classes generate a Chow group is slightly easier, and this is a general reference. If you want to know more about this topic, there is a very good new book by Eisenbart and Harris. I think the title is 30 to 64 and all that. Okay, so a very original title. Okay, so so now an example. So we, as always, as an example, we take the projective space. So anyone knows affine pieces that are in this? Can you somehow cover it disjointly with affine spaces? How would you define UI, anyone? So points such that something. Well, so the important thing is that every point in a projective space has a first coordinate that is non-zero. Yeah, because it has to have some coordinate. So there are a few that are 0, and then there is one that is non-zero, and then there is whatever. Yeah, xi plus 1 up to xn. And there are I of those here. Okay, and this is an affine space because the x's are arbitrary. Okay, and this is the UIs provide a disjoint union. A disjoint union of UIs give you an X. Okay. Now, what's the closure of UI? Again, anyone? You can tell me either with points or abstractly what is the subvariety.
So it should be the same, but allowing that one to be a 0, right?
Exactly. So you put anything here, anything here, anything here, and that's what? that's a projective subspace. Yeah, you just set a few coordinates to 0, and the other coordinates are arbitrary. So what you get is Pn minus I inside Pn. So I promised you to tell you that the ring of that the Chow group is really generated just by a class of a projective subspace in the projective space, and that's it, because this is what we were calling Xi. Okay. This is just the intersection of I hyperplanes in Pn. Okay, so we know the structure from the theorem of the Chow group, and we also know how they intersect, because in this case we can put them transversally. Okay, generically transverse. If we take two projective subspaces that are general, then they will intersect transversally. Okay, questions about this? Okay, no questions. We go to the next topic, partitions and Young diagrams. Diagrams. Okay, so a partition lambda will be a non-increasing sequence of non-negative integers. So we will denote it like lambda 1 up to lambda n of non-negative integers. Okay. Now the length is length. So the length of lambda, I will just say it's the number of elements in the sequence. It's n, and the weight is the sum of lambda i's. Okay. Now to each partition or a partition, it's typically in algebraic combinatorics represented by a Young diagram. And the Young diagram is not something you define, it's something you draw. So I will just define it through examples. So if I take the partition 3, 3, 1, the Young diagram, so I look at this 3 and I draw 3 boxes next to each other. Then I pick a next number, it's also 3, so I draw 3 boxes next to each other. Yeah, and if I have a 1, I draw 1 box. You have to be slightly careful with zeros, because if there would be a 0, we will sometimes need them, sometimes not. Maybe one more example. So for me, this Young diagram would be the partition 2, 1. Okay. So does anyone want to see more Young diagrams or more partitions? It's just a handy combinatorial tool to work with partitions. Okay, so we continue.
You mentioned 0. How would you draw 0?
No, you don't draw 0. So you somehow have to say how many rows you want this to have.
Sure.
Okay. Or otherwise, you would have to exclude 0 from your partition.
Sorry, Mateusz, did you ask for the Okay, sorry, the partition is not increasing. I lost that. Okay, so yeah, you always get something like connected.
Yeah, so you always get something that looks like that.
So I sometimes like, if I need the zeros, to draw like the line at the left of the diagram, like a bit further down.
Oh yeah, some people draw this,
yeah,
but then you also have to put some marks here to know how long is this line.
I mean, often we don't need them, but sometimes we do.
Okay, so actually Young diagrams, partitions, but also subsets of integers are the same. So there is a bijection. between partitions of length n and subsets of cardinality n. Of integers. And it goes like this. So we define I of lambda to be the set. So the smallest one we don't change. The next smallest one, well, it could have coincided with lambda n. So for it not to coincide, we add 1. Then the next one, well, it could have coincided. So for it to not coincide, we add 2, and so on. And for lambda 1, we add n minus 1. Okay? And it goes the other way around. If we have I, the subset of integers, assuming I1 is smaller than In, then we have lambda of I. Well, we know how to reconstruct it. So we just take In minus 1, In minus n minus 1, In minus 1 minus n minus 2. I see a typo in the notes. I will have to correct it. I2 minus 1, I1. Oh, and it's a partition. Okay. So somehow the smallest one you don't change, and the others one you adjust so that it becomes a partition. Okay. So this is just to...
Then the subsets, like they are ordered subsets, right? I mean,
well, it's a subset, so subset of integers,
subset.
so
Okay,
you can
yeah,
order it.
Yeah.
It's not an ordered subset, but I somehow have to say what I want, so I say I1 is the smallest one.
You're just spreading the numbers around so that you don't get a multiset.
Exactly.
Somehow.
So if you start from a multiset, you have to spread them. If you start from a set and you want to get the multiset, you have to squeeze them. And this is the only thing I'm saying on this slide, nothing deep. Okay, we continue. So I am assuming that people are to some extent familiar with the Grassmannian. So recall that the point in the Grassmannian GKN, well, this corresponds to a K-plane in Cn. But it's often represented by a matrix, a K by N matrix. So let me call it M lambda. It's a K by N matrix whose rows span lambda. So lambda equals row span. Yeah, so if you saw the preliminary lectures and so on, this M lambda is not unique. So it uniquely determines lambda, but lambda does not determine. You can do row operations, and because you can do row operations, there is a unique one where this is, I think, called the reduced echelon form, and it looks like this. And here is a 0, here are 2 zeros, here are 3 zeros, but here are arbitrary things. Okay? So each time you give me a lambda, I cannot define M lambda, but I can define the matrix like that.
Wait,
okay?
So we got a question in the chat that I didn't see. The question is, don't we just get subsets of non-negative numbers with a lambda?
Oh, sorry. Of non-negative numbers, subsets of non-negative integers. That's true. If I wrote of integers, that was wrong.
Yeah,
it was supposed, and I see I put here too many x's. Okay, it should be like that.
That a bit late.
I hope now every row. Yeah. So this will be subsets of non-negative integers. Okay. So notice that I can now group my matrices according to how far they are pushed here, the ones. So I can stratify my Grassmannian according to how the point that represents it is, I mean, how far the ones are pushed. Okay. So let me okay, so this matrix is in the notes given by a lambda. So okay, maybe I can put here the definition, a formal definition. So let lambda be a partition, that fits in a k times n minus k rectangle. So this is what I will be saying for future, but because this is the first time I say it, I will say what it means. It means that the length of lambda is k, and lambda 1 is less or equal than n minus k. Okay, so that the Young diagram actually fits in such a rectangle. Okay, and now to that I define a Schubert open cell. Schubert open cell. So you should think about this as our UIs. This is well, those points of the Grassmannian, such that the matrix, well, okay, so this breaking points, I think they are called pivots. Of a lambda are yeah, so here we have this, and this, okay, are in positions I of lambda. Okay, so this is a subset, and I want this subset to correspond to the lambda, yeah, to I of lambda, to be equal to I of lambda, so to correspond to lambda. I will give some seconds to copy this, and then I will do an example on G24, which is the first non-trivial example, okay? Okay. So we are now doing the example of G24. So we will be dealing with 2x4 matrices. So first, people sometimes denoted empty set. Formally, I think in our notation, it should be 0, 0. And here to 0, 0, you will get the first column, the 0th column and the first column. So it means that this looks like this, and these entries are arbitrary. Okay. Now, the another one is where we take a box, or formally we take 1, 0, open cell. And this tells us that first you don't shift, but the second one you shift by 1. Okay, and here we have an arbitrary thing, here we have 0, here we have an arbitrary thing. Okay, sigma, maybe I will give one more. I will not give all of them because that would take too much time. They are all in the notes. So this would be sigma 2, 1. Yeah, and this means that the first one we shift by 1, and the second one we shift farther by 2. Okay. So these are those that look like that. But in particular, notice that this is a C4. Yeah, this is a subset of the Grassmannian that is isomorphic with C24. This is a C3. This is a C. Okay, because the stars can be arbitrary numbers. This is exactly the same as in the projective space. And in fact, projective space is also a Grassmannian. So what we did for the projective space is even formally the same as what we are doing here. Okay, so so these varieties U lambda 0 form an affine stratification of the Grassmannian. Okay. So if you heard about Schubert cells, these are exactly those varieties, their closures. So open affine cells are those Schubert cells that we have defined, and Schubert subvarieties are their closures. Okay. Now here you could worry about the condition, what is the closure, but again, it's not different than from the projective space. So I can even tell you that this is a disjoint union for rho smaller than or equal to lambda of E rho 0. Now, what does it mean that rho is smaller than lambda? It means component-wise. So the first entry is smaller or equal than the first entry, second entry is smaller or equal than the second entry, and so on. Okay, so think about it. First, think about why this is true for a projective space that we discussed in detail, and then for a Grassmannian, it's really not very different.
Can I ask a question?
Of course.
So here you're representing points in the Grassmannian with like 2 times 4 matrices.
Yes.
So this is true up to action of G.
Up to rho, but once you make this reduction, this rho echelon form, this becomes unique.
Okay, I see. So
because, well, okay, if the first column is 0, then it's 0. If the next column is non-zero, you can make one entry equal to 1 and kill all the others.
I see.
And you proceed, and this gives you a unique matrix, a unique representative. This is very similar to a projective space. If you have a point in a projective space, you cannot represent it. But if you look which coordinate first is equal to 1, you can rescale the coordinate so that it becomes 1, and then your representative becomes unique.
I see. Thank you.
Okay, so the good news, we now know the Chow ring of the Grassmannian. Yeah, A, G, K, N has a Z basis, made by Schubert classes. So this we will denote sigma lambda. Well, by definition, this is the class of sigma lambda, where sigma lambda is the closure by definition of sigma lambda 0. Okay, so these are more complicated subvarieties than in the case of projective space, but well, they are still subvarieties and they are nice, and their classes are easy because they are indexed by Young diagrams that fit in a rectangle. So everything we do is combinatorics. Okay. Now in the notes you can find one more definition of sigma lambda based on complete flux. Sigma lambda, another definition based on complete flux. So sometimes this other definition could be good for exercises. In principle, yeah, for the sake of time, I will skip it. Okay, so now let me, but please take a look if you have like 15 minutes after the lecture. Oh, okay, I cannot make a new page. Apparently there is a limit of 20 pages. What do I do? I will disconnect and reconnect.
I think it's probably a good moment to stop for questions anyway, and then
yeah. So I will not disconnect my Zoom. I will just stop share.
Yeah.
I think this should work.
So feel
But
free
please
to
ask
ask
questions meanwhile. This didn't work.
So can I also think of, rather than the Schubert classes being indexed by these Young diagrams, can I think of them being indexed by just like subsets of the columns?
Yes,
Okay.
that's exactly the same.
Although
most
size
people,
K or yeah, okay.
Yeah, so most people I think of them. Yeah, so you are basically choosing a first minor from the left that is non-zero, and this is what they are. Okay, I have problems with doing this. I never went over 20 pages in a lecture. Apparently restarting didn't help. What can I do? Can I somehow delete everything?
You can make a new Jamboard.
Do you know how?
Yes.
Whiteboard, redo.
Wait, are you using
clear all my
Jamboards?
drawings? Clear all drawings. Okay, I can now continue. It's lost forever, but okay.
Well, no, it's in the recording anyway.
Okay, so now we will talk about sure polynomials and symmetric polynomials, a very important topic. So what do I mean by the ring of symmetric polynomials? Oh, lambda is a bad letter for that. I now realized, because this is how we were denoting Schubert classes. So the group of permutations, just permuting the variables, act of this ring, and I take polynomials that are invariant with respect to this group. So for example, x1 plus xk, if you permute xi's, this is good. But for example, x1 plus x2 squared, this is bad. Yeah, because for example, if I change x1 and x2, I will get a different polynomial. Okay, so I will describe a linear basis of this vector space. It's also a ring, but it's a vector space called sure polynomials. And their definition is not trivial. There are a lot of equivalent definitions. I will just give one. There is a big chance that other definitions will appear during other lectures. So let lambda be a partition of length k. So k is the number of variables. And we define the sure polynomials. Define sure polynomial as lambda as a quotient. So it's a polynomial, but it happens to be also a quotient of two polynomials. Well, you know, sometimes a polynomial is divisible by another polynomial. It happens rarely, but sometimes happen. So in the denominator, we just have Vandermonde. So 1, 1, 1. Then I have x1, x2 up to xk. And then I have, well, in the top one, I have x1 to k minus 1 up to xk to k minus 1. Okay, and in the numerator, I have pretty much the same, but I shift powers according to lambda I. So I start with, so this one is really x1 to 0. So before I had x1 up to xk to 0, now I put them to lambda k. Okay, and as I go row ups, I increase by 1. But here the powers also increased, so I change the lambda and increase by 1. So the last by 1, for example, will be x1 lambda 2 plus k minus 2 up to xk lambda 2 plus k minus 2, and the top row is x1 lambda 1 plus k minus 1. K lambda 1 plus k minus 1. Okay.
So sorry, can you write a little bigger than that? Because I have a hard time actually finding out.
So is it fine in the denominator or not really?
Yeah, I mean, there are
So
not
this
so
is
many
1 to 1.
exponents. Okay.
And here, this is to power k minus 1.
Okay.
Yeah. And in the middle, there is like square, third power, and so on.
Okay.
And upstairs is the same. Just to the top row, we add lambda 1. To the second top row, we add lambda 2. To the last row, we add lambda k. So here, what we are getting is xk to lambda 1 plus k minus 1. And this k minus 1 is this k minus 1. Okay.
So note that these exponents are precisely the ones from the eye of lambda. From
exactly. So they are made so that the rows don't become equal, because then the determinant would be 0. Okay. Okay. Now an easy exercise. Oh my. This wasn't as clever as I thought. Okay. So the degree of S lambda, this you can treat as an exercise. It's actually not so difficult, that this is the weight of lambda. Okay, the number of boxes of the Young diagram. And I think there is probably time for examples. With this definition, it's actually not so easy to see those examples, but not impossible. So if we take S and then we put like this A boxes, then this is known as the complete symmetric polynomial. We will denote it by HA. And this is just a sum of all possible monomials, xi1 times xik, xi. Oh, actually, there is another typo in the notes. So if we have A here, this should be of degree A. So we should have A of them, and it should be the sum should be over I1 less or equal than IA. Okay, this is called a complete homogeneous polynomial. Okay, and there is one more, namely if we put the boxes like that, again, A of them, and this we denote by EA. This is known as the elementary symmetric polynomial. And this is the sum of all monomials, but those that don't have squares. So it looks pretty much the same. Here, I1 is smaller than IA. Maybe you want a more explicit example. So maybe someone can tell me what is S. I put 2 boxes here, and let's say that I have 2 variables, x1, x2. So anyone brave enough to tell me what is this polynomial? I mean, wrong answers are good answers. It's recorded, so it will stay forever, but don't worry.
You're not the best motivator, are you?
Imagine, if you say it wrong, you will remember it till the end of your life.
That's exactly what I meant.
Alessio, then you maybe.
You get x1 squared plus x1 2 plus x2 squared?
Exactly, yeah. And if I change this to the, if I would put this, then only this one would survive, because x2 squared, okay. Sorry, I will leave it for a second. Okay. Okay. So in particular, notice that this is in k variables, but in order for this to make sense, A has to be at most k. Otherwise, it does not make sense, because we assumed the partition to be of length k. Yeah, so we can always extend by zeros, but if it's too long, then there is nothing we can do. And also the polynomial doesn't make sense there, because there are no non-square monomials of degree higher than the number of variables. Okay, I continue. I will be now super fast with clearing this. Okay, so so it's slightly like with Chow rings, and it's not a coincidence that I make this analogy, as you will see in the next lecture. So we have a very nice basis of this ring of symmetric polynomials. Yeah. So it turns out that these S lambda form a Z basis, form a C basis. So if you put Z here, form a Z basis. Yeah. In other words, every symmetric polynomial is a combination of sure polynomials. So now just as with Chow rings, we ask what's the ring structure, because you can also multiply invariant polynomials. So we can take S lambda, we can take S mu. Well, it's a symmetric polynomial, so it should be some sum S nu, possibly with some coefficients. And I will call this coefficients. They depend on nu, lambda, and mu. Okay. So these are some integers. And this is a sum over nu. Okay. And it's not clear what are those integers. So there is good news and bad news. So this C lambda mu nu are known as Littlewood-Richardson coefficients. And there is a Littlewood-Richardson rule that is a completely combinatorial rule on Young diagrams that tells you how to get this C mu lambda nu. Okay. So this is the good news. The bad news is that I decided not to give it. And you can find it in many places. In particular, we give a reference to Fulton Harris. Fulton Harris also don't give it in like the main part of their book. They do it in the appendix. And actually, it's also on Wikipedia and so on. So there are many ways where you can see this combinatorial rule, how to compute it, what you have to count. On the other hand, I will give it in two special cases. And first of all, these two cases are in particular enough to do any multiplication. And second, they are also much easier than Littlewood-Richardson rule. So I believe that it's good to know them. Okay, so a theorem. This is known as the Peary rule. So it tells us how to multiply any sure polynomial times the thing that has only one row. Well, then the coefficients are either 0 or 1. So it's just an honest sum of certain sure polynomials. But what's the sum? The sum is over all Young diagrams Young diagrams mu obtained from lambda by adding at most one box in each column, by adding n boxes, at most one in each column. Okay. Now, the one thing that I didn't actually write in the notes, and I should stress that if we work with k variables, we should also disregard Young diagrams that have more than k rows. okay, because we only defined a sure polynomial on k variables if it has at most k rows, if it's a partition of length k, okay. And another completely dual to this Peary rule is if we multiply also any polynomial, so but now we multiply it by 1, 1, 1, 1, 1, 1, let's say n times. So here I'm assuming that n is less or equal than k. And again, it's multiplicity free. So those CIs are either 1 or 0. Okay, but now the sum is over all Young diagrams mu obtained. So everything is as above, obtained from lambda by adding n. This is n. Oh, my handwriting is far from perfect. N boxes at most. So I'm just writing as above, at most 1 in each row. Okay, and we will finish with an example. So, sorry, 5 seconds. Okay, so this is Peary rule. It tells you how to multiply special sure polynomials. Okay, so an example. And because Alessio is very unhappy when I make small subscripts, I will sometimes, instead of doing this, I will just write this. Yeah, that's much easier to see. Okay, so currently I'm multiplying sure polynomials, although I am not using s. And I'm multiplying this. Well, I don't tell you what's the number of variables. It's actually it doesn't matter as long as there are 3 variables. And then, well, what happens? This is my lambda. Oh, I know what I will do. I will draw it in red. So I have to start with the red lambda. And then I have to add 2 boxes, at most 1 in each column. So I can, for example, add them here. Certainly, I added at most 1 in a column. Where else can I add them? I could add them here and here. Where else could I add them? I could add them here and here. Where else could I add them? I could add them here and here. Okay. So this is a rule how to compute the product of 2 polynomials. Yeah, so you should read it that the product of these 2 polynomials is a sum of those 4 polynomials. I encourage you to check it on examples. Okay, so with this example, I would like to finish this lecture. And for every lecture, apart from the exercises I was leaving you, like, for example, look in the notes, complete the proof, and so on, we also with team prepared some exercises at the end of the chapter. And they are not trivial, and Tim was complaining that this can discourage people from doing anything. No, I think this should encourage people to really work on those exercises, spend time, and if you have any problems, just let us know, and we will help. We will definitely help. And these exercises will be really important to understanding following lectures. So if you feel slightly lost, then you have to do all of the exercises. Okay, thank you very much. This is all. Tim is saying something, but we cannot hear you.